Well, better late than never. Forgot to turn that thing on. What's that? That's not good. Yeah, that's right. Plus 2.25 minus 1.5. So if you want to see what we did here, you'll have to go back and look at the notes and kind of follow it on your notes. Minus 1.5 kips minus the force in kj. And so the force in kj is equal to, what is that, 0.75 plus, on this side, 2.25 minus 1, I guess that's right, 0.75 kips. Next, we already decided some of the forces vertical wasn't very profitable. So we're talking about some in moments about some place. How about some moments about this point right here? The only reason I picked that point is two unknowns come through that point. This point also would work. Two unknowns come through that point. Any other place would give you an equation which would be useful later, but not right away. So, what the heck? Let's just some moments about, it's got a name anyway, some moments about K. Sum of the moments about K is equal to 0 is equal to 0.375 times 12 plus minus 1.5 times 6 minus plus V2 times 12. Who's got a calculator? Getman, you got a calculator on you there? You can listen to music, but you can't calculate, huh? Bad choice. Therefore, V2, well, if I'd have made a mistake, you guys would have caught it by now. Let's see what V2 is. We'll cheat. 0.375 kips. No, let me see. Look at the wrong one. Still is 0.375? Thank you. 0.37. I thought you didn't have a calculator.
Oh, I listen to my music. It's over.
Yeah, you got your head on wrong. There's no question about it. When music starts telling you answers to engineering questions, you'll be rich. All right. And finally, now that we know that, we'll go list it, 0.375 kips. And FEH, we'll get that from sum of the forces vertical, is equal to 0, is equal to minus 0.375 minus FEH plus 0.355. Thank you. I wonder why people do that. Tell people about their mistakes, I mean. All right. Well, you know, it makes a little more sense, doesn't it? It's in the middle, doesn't have any axial force due to the horizontal loads. And that probably makes some kind of sense. This guy's kind of prying down on it. This guy is prying up on it. And it turns out to be 0. Won't always turn out to be 0, especially on the final when I make this guy 3A, 5A, and A. You know, then things will come out goofy, and you'll have to crank it out. And so, F sub EH is 0, equals 0. And did we already get F sub KJ? Yeah, 0.75. All right, now I think you see where I'm going across the top floor. The next thing I'm going to do is I'm going to pick out the next floor. Again, I'm going to pick it through points of 0 moment that are assumed. And I'll tell you what I'm going to do first, just to make sure you see what I'm doing. Let me pick off the top 2 floors first. And then we'll pick out this second floor. On this one, we have 3 kips. On this floor, we have 5 kips. That's why I didn't mind if we added an extra floor with another 8 on it, because it's not going to change any of these numbers. And this one was 12 feet, and we've pulled off 6 feet. A little more to scale. And these horizontal forces will be resisted in proportion to the size of the columns. So this guy will be an A, this guy will be a 2A, this guy will be an A, for a total resistance of 4A is equal to 8. And I guess that's 2 kips for each A. 2 kips, 4 kips, and 2 kips. As a matter of fact, I don't think I really have to pull out that middle floor. It'd probably be easier just to go ahead and take the whole top of it. Let's see if, I don't think that's going to work. Because I have no moment, and I have no moment, and I have no moment, and I have an axial force, and I have an axial force, and I have an axial force, and I don't know 3 things, and I'm not going to be able to solve for those. It's like a statically indeterminate structure with 3 vertical forces on it. So I am going to have to pull this middle piece out. This would be the force in member GF. This would be the force in member HE. And this would be the force in member ID. And as you see, it's like anything that's got 3 supports on it, it's going to be statically indeterminate as it is. So let's pull this piece right here out of the structure. Looks like so. It's got 5 kips on it. We already found these numbers here. We know there's no moment at the pin, no moment at the pin, no moment at the pin. The force on this joint was 0.75 pushing to the left on the upper part, so that is 0.75 to the right on the other part. F sub LG we solved for was 0.375 down on L, and therefore 0.375 up on the other side of that joint. Getman, you got that direction right. And here's a shear and an axial force, and a shear and an axial force. The shear was unknown. We assumed it in proportion to the size of the column, and it picked up 2 kips of force, and now I'm ready to go. I see 3 unknowns, and I know I got 3 equations of statics. Call this guy, guess what? 0.75 and 2, this guy's winning. This force actually goes to the right. This guy's in tension. Question? Minus the 5. This guy's in compression. Thank you. And his name is, who is he? GH. And therefore, sum of the forces in the horizontal direction equals 0 is equal to 0.75 plus 5 minus 2 minus the force in GH. And the first thing you see is why people do this, because it's a quick and easy way to find out reasonable sizes for these things just to get started. 5 minus 2 is 3. 3.75, is that right? Thank you. Kips. Equals 3.75. You probably do well as soon as you solve for a force that's unknown is write it down. The reason you ought to write it down is because then you no longer think it's unknown. Now, the reason you do that is because you no longer think it's unknown, because otherwise you think it's unknown, and you don't want to think it's unknown. Lane, why would you do that?
It's unknown.
That's pretty good to get, to be totally asleep like that and snoring and drool running out of your mouth. That's a good answer. All right, 3.75. Now, seems like we're getting the hang of things. The next thing is going to be a sum of the moments equation. Sum of the moments about the joint always seems to cough up an answer rather than wander around and do different legal things. Just always some moments about joint G. Known force, no moment arm, no moment arm. No unknown force with a moment arm, known force with a moment arm. That ought to work. Let's call this guy here the shear number. There'd be a 1, 2, 3. This would probably be the fourth one once we got back to it. And this is the force in member GF. So some moments about G is equal to 0 is equal to. All right. Did you already get me an answer? Well, the answer's in the book, isn't it? All right. Let me write it down. Some moments about G is minus 0.75 times 6 feet plus shear number 4 times 12 feet minus 2 kips times 6 feet. Is that everybody? 1, 2, 3, through the point, through the point, through the point. And you said V sub 4 is how big? Thank you. Did it turn out in the proper direction? Okay. 1.375. And sum of the forces vertical now. Sum of the forces vertical is equal to 0 is equal to 0.375 plus 1.375 minus the force in GF. And so you know that. Force in member GF is equal to 1.75. Thank you. Okay. Now then, will the shears and the axial forces influence your design? To some extent. Most of the problems occurring in a frame like this are due to bending. So let's just say we're going to try and design member GH. Design member GH, make it out of A36 steel. I'm going to tell you the allowed stress on A36 steel, and all these numbers, have other considerations, lateral torsional buckling and all that kind of stuff. But just plain old 305 type of design. Let's say it's equal to 36 KSI, which is the yield stress, divided by 1.67. Is a reasonable factor of safety that allowed stressed people throw on these things all the time. The equation for bending is what? Equation for bending stress, green. See, one green always says maybe he's talking to the other green. But the one green's pretty smart. She just keeps her head down and keeps writing. She doesn't look up. Green, on the other hand, I got his eyes. Remember the equation for bending stress in a beam? I mean, I know it's been a while, Booth. MC over I is correct. What is the equation for torsional stress in a rod? These are really things you ought to TC over J is correct. I notice that many of you are getting tattoos. It says Alicia, or something like that. Believe me, in 2 or 3 years, you'll be over there lasering it off. If you'll get sigma is equal to MC over I, it's always good. You will never go wrong. And that's equal to M over S. What is S? The section modulus, that's correct. And therefore the section modulus that is required is equal to the bending moment divided by the allowed stress. What is the bending moment on member GH? .375 times 12 feet. In other words, you see the free body right here. It's a shear. It's applied to the beam, and it causes a bending moment at this point. And therefore, 1.375 times 12 feet, 1.375 kips times 12 feet. You really should always put your units in there because you'll see these feet hanging out. And when you divide by an allowed stress of 36 kips per square inch divided by 1.67 to make it a safe stress, you'll right away see, oh, there's feet running around here, times 12 inches in a foot. That says that the required section modulus that you need to go look up in the text is equal to 9.181, 85, okay, that really doesn't matter, those numbers out in there, inches cubed. Now, I don't know where these loads came from. 3 kips is no load at all. 5 kips is no load at all. It'll probably be more like 30 or 50 or something like that. So I don't even think we got a beam that small, but we can look and see. Yeah, we might have to go to a 305 book to get a list of section moduluses, a section moduli. Yeah, he's just not interested in design in this book. Anybody in here that's retaking 305 at the same time, and you brought your 305 book with you? Didn't bring it? All right, well, anyway, if you remember, there's a shape like a W12 by 50, and then there's a W12 by 53, and then there's a bunch of W's, and over here is a moment of inertia, and over here is a D for the depth, and over here is a section modulus. And there's an XX value, and there's an S sub YY value, and you will, without a doubt, stand the beam up about its strong axis, and you'll come around in here until you find a section modulus that is at least this big or bigger. And if you remember also, your wide flanges run in ranges. There'll be a bunch of W12 bys. There'll be a whole set of them. And there'll be a set of W15 by, and a bunch of W18 by, and a bunch of W21 by, and 24 by. And what you do is you come down in this set right here and you pick the lightest one. For instance, if W12 by 50, actually would be on the other side of this one in the table, was the lightest one, you put a circle around it, that's a possible choice. Then you come down in the 15 by sections, and you'd pick out the lightest one, and you'd pick out the lightest one, and you'd pick out the lightest one. And then you'd call up the guy and you'd say, after you get to a certain size, they'll start getting none of them will be the lightest one. And so you call the guy up and say, I want a W21 by 42. You got such a thing? He says, I can get you one out of Chicago in 6 months. Okay, got any 18 bys? The guy says, yeah. So you got an 18 by so-and-so? He says, yeah. That's the least expensive one. In 305, the cheapest answer, the best answer, the right answer was always the lightest one, whether it was available or not. All right, so that's how you use it, and that's just how quick you can get an initial guess as to the size of these members. Now there's a second method. This method works really well on buildings that have a whole bunch of bays and not too many stories. A second method is what they call the cantilever method. And it's over on page 646. And it makes some assumptions also. And when the boss shows you something new that you weren't taught in here because it's only a 3-hour class, what are you going to do? No? Is that what you're going to do? Go to your office, and what are you going to go to my office? No. My office is all the way back in Bryan, and you're in Iraq. And the guy says, I need a quick design on this building.
Give me a week and a half.
You're going to look in the book, and you're going to dig it out. That's what you're going to do. Dig it out for me. Tell me the assumptions. Take a look on page 646. What are the assumptions in the cantilever method? Well, the support is where you distribute the loads as opposed to the horizontal forces. You actually distribute out the estimate of the values as the axial loads inside of these members as opposed to the horizontal shear carrying capabilities of these members. So in his case, he's got a building. He doesn't choose a real tall building because it's got too many pieces to it, and he just wants to show you how it's going to work. And in this one, with 4 columns in it, the first thing he's going to say, the first guy has got, let me see how much area he has. Instead of distributing it horizontally, we're going to distribute the axial forces as known as opposed to the horizontal forces. And pretending it's a cantilever, it should have stresses in the beam, assuming it's just a beam and it's sitting there like that with some load on it, like a cantilever beam. And these stresses then will go into the columns as loads. So in his case, number 1, cut the free body with the upper and lower halves of the attached columns, cut through the sections midway between the floors. We're still going to assume there's no moments in here, so that assumption is the same. And here is the stress in the cantilever, and here's the stress in the cantilever and the stress. What does he say for number 2? Look on page 646.
Number 2. Evaluate the actual force.
Evaluate the axial force
In each column at the point of inflection.
in each column at the point of inflection. I'm going where the point where there is no moment. You're doing great.
In a given story by equating the internal moment produced by the column forces
By the column forces. All right.
to the moment produced by all lateral loads above.
All right. So in other words, when we take this piece right off here, it supposedly causes stress in a cantilever beam. All right. So he's got an example. Let me check what he's got here. He's got, first off, here is the centroid of the cantilever beam. This guy has got 2 areas. This guy has got 2 areas. This guy's got an area. This guy's got an area. And therefore, the centroid of the cantilever is going to be in the center. If you had 2A, 2A, A, and A, how would you find the centroid of what he's calling a cantilever beam? Let's just say this was 2A, and this was 2A, and this was A.
You could think of them as like loads.
Exactly. Exactly. You'd simply sum moments about some point, and you'd say 2A times that distance plus A times that distance plus A times that distance is equivalent to 1, 2, 3, 4, 5, 6 areas times X bar, and solve for the centroid of the shape. And then you would put the point of 0 stress at the neutral axis of the cantilever beam. So this guy's load right here is out here. He just calls this dimension, this is 6 feet, and this is, no, take it back, that's 24 feet and 12 feet. So he just calls 12 feet like a distance. And so to find out how much force you have here, he's going to multiply that area times 12 feet, or times one of these lengths. And he says this force here is like 2 times A. Out here, 1L, 2AL if you like. In effect, the L's cancel. This one's out here a distance 1, 2, 3 of these dimensions times A, 3A times L, and 2A and 3A. All right, I'm going to do a free body. Here's a free body of the top half. It is 6 feet tall. It's got a column, it's got a column, it's got a column, it's got a column. It has a load which is tending to roll this thing about the centroid of the cantilever. 4 kips. Is that the same problem we had? I don't remember. Guess it doesn't matter. And we have on this side, if the force is pushing the thing clockwise, then on this side of the cantilever beam we'd have tension. And we'd have tension. And we'd have compression. And we'd have compression. And this distance is 24 feet. 24 feet. 24 feet. We have no moment, 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 no moment, no moment. And our forces here are 3 times what he calls sigma 1 times area, basing it in terms of stress. Yes, sir. The 3A, yeah. It depends on these A values. We assumed, or he assumed in this case, that the outside columns will carry about half as much as the inside. So he doesn't know what A is, and he doesn't want to commit to a number yet, but he'll put 2A at this distance from the center of the cantilever beam, which is 12 feet out. Now, he could go ahead and put the 12 feet in there. It wouldn't matter. The 12 would cancel in effect. But he just says, out here, there's a 2A at a distance L. So I got a 2AL. Out here, the stress is 3 times as big. You see how the moment of the MC over I, you see how the C distance is 12, but here it's 36? See how it's 3 times as far out? So the stress, if we're going to assume these are stresses, are 3 times as big, and then to turn it into force, you multiply times the area of the column itself. So equivalent, what I have is like 2A worth and 3A on the outside, and then the same thing on the other sides. All right, so he's going to call it 3 sigma 1A, 2 sigma 1A, 2 sigma 1A, and 3 sigma 1A in terms of stress. Then my question is, if you sum moments about this point, you ought to be able to tell me what those forces are going to be. Getman, how did he get them? No fair. Borrow his book. Tell me how. I want you to dig this out. I want to see you dig it out.
How to get the forces?
Booth?
Can you move it up?
Oh, I'm sorry. Thank you. Yeah, I'm looking for these forces.
Well, you could sum some moments.
All right. Go ahead.
Some moments about, I don't know about that corner.
Well, how about the middle? I don't care. I certainly can't complain with your some moments. The only thing is this guy's got the same moment over as that arm, and he's the same as him. Okay.
All right, so it's 4 times 6.
That's a good start.
Minus 4 times 6.
Okay. I'll go with the minus.
Yeah, plus 2 sigma,
Sigma
or
1A. He just
sigma 1.
puts it in terms of stress. In other words, I don't care if you write basically a 3 sigma 1A or a 3A. It's in terms of stress in the column.
Is that times 12?
Times 12.
Plus 3 sigma 1A times 36.
Okay.
And plus 3 sigma 1A times 36.
Okay.
Plus 2 sigma 1A times 12.
All right. Is equal to 0. And so I don't know what sigma in the columns are, but basically if we're talking in terms of stress, then I ought to be able to tell you what a sigma 1A comes out to be. How much does a sigma 1A turn out to be? I mean, I don't know sigma 1 and I don't know A. And so just grouping that as a term in terms of, see, this is a force. That's why I put the sigma 1 in there. Stress times area would give me a force. He's working. I see his thumb is moving. 0.091. All right. Sounds good. What is 1 over 11? Okay, that's all. He didn't put the .091. He put 1 over 11. I'm just checking. Howdy. Where have you been?
Wait on a ride?
Wait on a riot? Did the riot occur?
They were late.
All right, so we know what sigma 1A is, and therefore 0.091. Getman?
Yeah.
Now what do we do?
Divide by the area.
Well, actually, you have a force here,
Oh,
and so
you're done.
you're done. Give me the numbers. We said that in terms of stress times area for force in the column, that a force of some magnitude ought to do the job.
Oh, so that's the force for the first column.
Correct. So,
Oh, it's 3 times that,
just that simple.
and 2 and 2.
All right, give me that number. I can cheat. Thank you. But I'd rather see it come out of your calculator to make sure you see it. And 2 of them would be 91 is 2, 99 is 18, carry 1, 0.182 kips. And 0.182 kips. So what we're saying is the stress in these columns, if you put 0.273 kips divided by area, let's just check it out. If you put 0.273 kips over A, you would get a tension stress of 0.273 over A stress. What happens if you take 0.182 kips and divide it over 2A? 0.091. Same thing here. And same thing here. That's what we're saying. That was the assumption. The assumption was that when you bent the cantilever beam, the stresses you would cause in the columns would be linear. And they would have a neutral axis. And the neutral axis would occur at the centroid of the columns. And now we're ready to go again. Just as boring, just as dull. You guys didn't miss a thing. And now then is that thing the same? I don't remember what the other one looked like. There's the other sheet. No, the other one had 3 kips on it. Phooey. Well, that's all right. I'd like to see. I'm kind of curious as to the difference. But there is a difference. In other words, the 2 methods work well. Portal method works well when you have a lot of bays and a relatively short 2, 3, 4 story structure. And this works really well when you have maybe 10 bays and 50 floors. It comes out really nice, really close. All right, 12 feet, 6 feet, 4 kips, 12 feet, 6 feet. Getman? Well, I haven't got it yet. I'm just preparing you. But I notice you're ready for anything. I'm sorry. Do I have a moment? On this one, just on this piece right here. See, here's what we've got. We've got hundreds of unknowns in this thing. We got rid of a lot of the unknowns by not a bad guess of assuming there's no moment in the middle of the column and no moment in the middle of the girder. Let me put it up here where it's a little more to scale. Then the next thing is you still had too many unknowns. And so you decided to distribute the horizontal shear forces in proportion to the size of the members. Or you decided to distribute the vertical forces in proportion to a stress distribution that you used to see in a cantilever beam. So I've done that. Now I'm through with the approximations. Good, bad, or indifferent, whatever, I'm ready to go with this method. So now my question is, here's the free body. Getman, what else do you want me to put on there?
Put that 0.273.
That's all I was really, that's what I was really making sure. 0.273. And not so much if you know it, but if all these other bozos know it. And now then, here is an unknown shear number 11, and here's an unknown shear number 12, and here's an unknown axial force, the force in member AB, and we do the same thing again. Not much to it.
What if the load has changed?
Well, you're going to have to run the analysis again. Yeah, well, sadly, yeah. If you decide the wind loads have a different combination on the structure than this, but, you know, hopefully you're going to put the max wind load on there and go with that. All right. Now then,